Good morning, everybody.
Good morning.
Thank you. Thank you for coming and finding your way downstairs. Welcome to ISDC 2026. I think this year we may have reached a critical inflection point in how we approach the challenge of space exploration. Of course, time will tell, but I wanted to share my take on this with you today. The question we'll be exploring today is whether space-based data centers launched by mass drivers on the moon are going to be truly transformative as a technology, and are they really going to help us become a spacefaring civilization? So let's start with what is a data center. Well, a data center is fundamentally a device that converts energy into wealth and power and heat. Technically, it's not a new idea. We've had supercomputing clusters for years. The details of what's in a data center, like the workloads and the hardware, these are constantly being reinvented. Now, by powering AI, data centers have become a new kind of economic accelerant. Now, what do I mean by an economic accelerant? Well, think of like lighter fluid being put on a barbecue. That's an accelerant, right? But other kinds of accelerants are, for example, putting fertilizer on a field. That'll help the field be far more productive. And in fact, this is something that was done a few hundred years ago when sailors went out and mined guano off of these islands in the Pacific Ocean and brought the guano back to fertilize crops. It was one of the first fertilizers. Whale oil is another example of an economic accelerant. They used it to power lamps, and those lamps allowed people to work later into the night, and that helped accelerate the economy. Satellite navigation is a more recent version. It makes transportation more efficient. So we've got these remote outposts for mining guano. We've got remote outposts for whaling operations. Like, you remember Shackleton found his way to a remote outpost on an island down in the South Atlantic. And satellites were another form of remote outpost. So the point here is that in pursuit of what I call economic accelerants, we are willing to establish outposts in hard-to-reach places. So as we analyze this idea of data centers in space, let's start with some assumptions just to set the framework a little bit. We have to assume first that latency-tolerant applications are going to continue to exist. So, for example, this is model training for AI, non-time critical forms of inference. These are not latency-critical applications. If they were latency-critical, we'd have to put the data center close to us on Earth, like an edge server. That's not what we're talking about. We also have to assume that demand for AI is going to drive up energy prices. Well, we're already seeing that. There's a lot of concern about that already. We also have to assume that the energy supply is constrained in some way, perhaps by regulatory burdens, or by not invented here, or by banana, which is built absolutely nothing anywhere near anything. If we find that there's constraints on the energy supply near the grid, then we could consider off-grid data centers, something like putting some data center far away from anybody else. So these are an alternative we need to consider, and I'll be considering those in a minute. But if we're looking at off-grid data centers, then you have to think, what is the constraint here? And I'd like to point out that the chips are really the bottleneck. If you have idle compute in your data center, that's very, very wasteful. It throws off the economics. So you have to have 24/7 power rather than intermittent power supplying a data center in practice. And for that, if you're going to do it off-grid and you're, say, using solar panels, then you're going to need storage so you can run the data center at night off the energy collected during the day. All right, so if you're going to make an off-grid data center, what's the best place? Well, one of the best places is called the Atacama Desert in Chile. It's a fairly high altitude, very dry desert. There's not much dust in that desert, so your solar panels won't need to be cleaned very often. The annual DNI, or I think it's direct normal irradiance, which means the amount of sunlight you get if you track the sun, is 3,800 kilowatt hours per meter squared, which is pretty good. But there's lots of places in the world which have similar quality of resource in terms of solar power. So there's some places around the world, such as the Western United States, North and South Africa, and most of Australia, which are also very good places to put off-grid data centers. So lots of space on Earth for off-grid data centers, so we have to consider this as a potential possibility compared to space-based data centers. So let's look at the optimal terrestrial power scenario. If we convert the power I mentioned from the Atacama Desert into watts per meter squared, you get 434 watts per meter squared. But the desert is cold, and so when you're in a cold space, solar panels operate a little bit more efficiently, they last longer, and you get a small efficiency benefit of 1.034 at the bottom here. This is how much extra power you get because you're operating your solar panels in a cool environment, multiplied by the efficiency of the panel. Now in space, the opposite is true. In space, the solar panels operate around 110 degrees C, so they get degraded in terms of their performance. And so that factor is 0.34 degradation, or 1 minus 0.34 is a factor. So You multiply the solar radiance in space, which is 1,361, by this factor for degrading the solar performance because they're hot, by the efficiency of panel, and you get a different number, which is slightly lower than the full radiance. So this is a sort of summary of all that. There's one more factor we need to consider, which is the time shifting. On Earth, you need to time shift your power from daylight to nighttime. That means pushing the power through storage, like through a battery, and you lose a little bit of power when you do that. So when you factor all these things in, what happens is terrestrial solar power ends up requiring 2.1 times as much solar panel area as you need for space-based solar power. So this is good. 2.1 times is a savings of sort for space-based solar power. It's not nearly as good as a lot of people who promote space-based solar would like you to believe. They often say it's 9 times better than Earth or something like that because they like to compare to a cloudy place in England instead of the Atacama Desert. But that's the sort of bottom line. Now, it's not the end of the story, though. This is just a solar. If you put your space-based data center in orbit and you listen to everybody else out there, they'll say, well, because we want to keep the satellite as light as possible, we'll minimize the radiator size and run the chips hot. And that means that the chips are going to operate less efficiently because they're hot in space, if you make that assumption. Now, we've actually studied this on Earth. We've transitioned from air-cooled data centers, which is this middle dot, to water-cooled data centers, which is this blue dot over here. If you do the opposite, you make the data centers hotter, then you end up over here. And what this graph is showing is the power the data center is drawing per node. So you end up using more power if your data center is hotter. And this is due to something called leakage current in the microchips. Similarly, the performance versus temperature, for the water-cooled data center, it's the best. For the air-cooled data center, it's a little bit worse. And for the space-based data center, it's worse still. So if you run all these numbers, you'll find that the extra power for the space-based data center is going to be 33% more, and the performance penalty is about 0.68. You'll get less performance. And you make a table of all this, do the calculation, and it turns out that terrestrial requires now just 1.07 times as much solar panel as you need in space. So it's not very exciting. It's kind of a wash. Now, mind you, you save this energy storage, but you've got to create a satellite, launch it, all this other stuff. It just doesn't make sense economically to put a data center in space with this 80-degree assumption. But I thought about this. Why are we assuming 80 degrees? Why are we running data centers hot? The reason they're doing this is because of the cost of launch. People want to make the data centers as light as possible, which means make the radiators as small as possible, which means make the chip as hot as possible. It's all being forced by the fact that launch is expensive. Let's ignore that for a moment and just say, let's optimize the data center in space and not worry about launch costs for a second. And if you do that, you can run the data center at, say, 0 degrees. It's cooler. And you actually get the benefit of the chips being more efficient, the power, they require less power. And it turns out that then, in that case, you need 5 times the solar panel area on Earth as you would in space if you can run the data centers cold, which is a logical evolution of data centers. We want to run them colder and colder as we go. Okay, bottom line, the goal here is, say, we target what we call low junction temperature, the chip temperature, of 0 degrees C. We say we launch sufficient radiator mass to achieve that target temperature, so more mass than most people are thinking. And then you get this GPU performance and power consumption both improving significantly over terrestrial data centers. Now you've got a place in space, if you could create the place, where it's exciting to send your chips and have them run there because they operate more efficiently, you'll get more money, more wealth and power by doing that. So now you've got a place you can send your chips that makes a lot of economic sense on a very, very large industry. It's this economic accelerant for the entire planet, just sending your chips, just the chips, to this data center that doesn't exist yet. But if it did exist, very cool. So now we have to say, okay, how do we make it exist? What is the trick to creating a space-based data center? We can do it by ignoring launch costs. That's one way to do it. But if you don't ignore launch costs, how do you do it? Well, let's talk about launch costs for a bit. The Apollo program, we know, cost from history $250 million per kilogram of astronauts and samples that it brought back from the moon. $250 million per kilogram. Now, obviously we've improved since then, right? No, we haven't. Mars sample return costs 60 times more. It's $15 billion per kilogram of samples returned from Mars. Way more expensive. It's technically slightly further to go, so that's part of the reason, but it's very expensive. And yeah, that's a hard reality. Now you think, okay, maybe it's just 2 data points. You start looking at more data points from all kinds of missions across the spectrum, you end up with a graph like this. And you can see that if you fit a line to this graph, it's an exponential relationship between the cost per kilogram of a space program, per kilogram of what it's actually trying to move around at the end of the day, and what I call the delta V, or it's technically the equivalent delta V. There's a paper I wrote on this term, equivalent delta V, but the delta V of the mission. So this is what space programs look like, empirically speaking. It's not surprising. This is a manifestation of what we all know is true from the rocket equation. The physics of the rocket equation say that the mass ratio is proportional to the exponent of the velocity. This is the empirical manifestation of that in the cost of space programs. So if anybody proposes a concept where their mission cost is deviating significantly from this line, it's very likely to be an aspirational idea, not a real idea grounded in economics. This line, these horizontal lines represent what it would cost to put your data center far from Earth, like the edge of this lunar space. It would be about $300,000 per kilogram to launch your data center from Earth and stick it out there at the edge of this lunar space, based on this empirical data. Maybe you get a little cheaper by doing a big data center, but Wright's law, the law of decreasing costs as you increase the volumes, only takes you so far. It doesn't take you to these exponential numbers like 1,000 times cheaper. One thing you could do is you could move the data center closer to Earth in the sun-synchronous dusk-dawn orbit, which is what this video from Scott Manley describes. This definitely lowers the launch cost a bit, but not nearly enough to change the economics. The other problem with this is that you're kind of in the flux of all the other satellites. So your data center satellites are going in one direction, all your other satellites are going around the other direction. They're going to be going through each other constantly, which is going to create an orbital debris flux that you're traveling through. Very likely you'll have a lot of damage to the satellites, and the heat and the radiators will start leaking. You'll be using a lot of propellant to constantly avoid collisions. You'll need a lot of propellant to deorbit these satellites. All this kind of degrades the economics significantly. And of course, you finally need to deorbit the satellites at the end of their life, put them back into the Earth's atmosphere. You're going to run into regulatory challenges and environmental concerns around deorbiting thousands and thousands of satellites every year if you take this approach. So what about this idea of NRHO data centers? So NRHO stands for non-rectilinear halo orbit. Non-rectilinear is like a highly elliptical orbit, and a halo orbit means the orbit goes around the Earth-Moon system, not just around the Moon. So the Gateway, for example, looks like it's orbiting the Moon, but technically it's orbiting the Earth-Moon system. And so it stays facing, the orbit faces the Earth continually as the Moon goes around the Earth. The advantage of this orbit is that it's always has a line of sight to Earth, so constant communications with Earth. It avoids Earth eclipses, so it doesn't get eclipsed by the Earth for long periods of time. And it gets eclipsed by the Moon occasionally, but about 10 times a year, and only for 20 to 70 minutes. So from a data center efficiency point of view, you're getting pretty much 24/7 solar power for your data center if you put it in this orbit. So as I said, data centers, workloads are constantly reinvented every few years. We're migrating from air-cooled to water-cooled to now possibly space-cooled data centers or colder still. We know it's hard to find a reliable cold sink close to a source of power on the Earth. You can go in the Arctic where it's cold, or the Antarctic, but there's no source of power there, so that doesn't really work. But maybe we can create this environment where there's a cold sink and a source of power at the same place by creating an NRHO data center. So the vision is offload all our latency-sensitive compute to this NRHO data center. Think of it as a growing facility over time. It gets bigger and bigger as we launch more mass into it. We manufacture it, this is the key point, 99% of it is manufactured from materials we mine on the Moon. And maybe 1% of it, like the chips, for example, are launched from Earth and sent to the data center to be run. So the advantage of this, the economic advantage of this, is this huge economic accelerant is able to extract more power per chip that we produce and sidesteps many of the regulatory challenges on Earth. So there's this huge economic drive to do this. Enormous trillions of dollars related to this being a successful endeavor. The disadvantage, of course, is how do we get this mass that we need to make the data center into an NRHO orbit in the first place. And this problem can potentially be solved by constructing a mass driver on the Moon. So let's talk about mass drivers now. So I've presented at ISDC before on terrestrial mass drivers. So this is what a terrestrial mass driver looks like. It's got a horizontal section, this one's in the ocean, that accelerates the spacecraft at very high velocities. It's got a ramp section which sort of steers it towards the sky. It's got an elevated evacuated tube which helps the spacecraft get to the densest part of the atmosphere. And finally the spacecraft travels through the upper part of the atmosphere using a heat shield and a rocket to keep it going against the remaining amount of atmospheric drag you've got. This whole bottom part is a long evacuated tube. And this technology, we have a cost model for this. It costs about $35 billion to build one of these, according to our cost model. So it's well within the range of what's possible with space programs today, which are in the hundreds of billions of dollars typically. A lunar mass driver, on the other hand, is a much simpler idea. It's got a horizontal section, much shorter, because you only have to go to about 2.35 kilometers per second to get off the moon into an NHRO orbit. It maybe has a very small ramp section to stop you from hitting some mountains. And then there's no elevated evacuated tube. You might need like a dust cover to prevent dust from getting into it, but you don't need to keep a vacuum up there because there's already a vacuum on the moon. So that's a much easier idea. Of course, you've got to build an industry on the moon to make this possible. The economics of mass drivers are very interesting, and this is some key takeaway, because you have to explain why have mass drivers not gained traction up until now. So let's look at the economics of mass drivers. We already have mass drivers on Earth. They're used on Ford-class aircraft carriers on a small scale. They accelerate airplanes off the aircraft carrier. If you were to scale one of those EMALS systems up to space launch speeds, and I've attempted to do this, you end up with a curve that looks like this. The slope of this curve is cost is proportional to velocity cubed, and I'll explain why in a minute. Roughly, this is the position of the curve. Now, if you were to say, okay, I'm going to build a mass driver, I'm going to extend EMALS to be a large enough mass driver to supply the International Space Station. If that's your proposal, then your delta V to get to the space station is around here where this arrow is. And if you do the math on it, you'll find that, oh wait, it's cheaper to use rockets to get to the International Space Station, given the volumes of stuff we need to send there, than it is to build a mass driver. So it's like 100 times cheaper, in fact. So anybody proposing a mass driver to resupply the ISS is going to get laughed out of the room, because it doesn't make sense. But if you shift your focus from resupply the ISS to, let's say, put a mass driver in a factory on the moon, let's settle Mars, that kind of stuff, well, then your delta V moves over here to this range, where rockets have become a lot more expensive. And if simultaneously you take a step back and say, well, the electromagnetic launchers on the Ford-class aircraft carrier are an old technology already, a lot of people have focused on new ways of making mass drivers accelerate things linearly. And the best technologies in that regime right now are now able to achieve an acceleration that's proportional to the square of the exit velocity, not the cube. And I'll explain why in a sec. Then you get to this relationship here, where the new cost of the mass driver is down here, and our target market puts the rockets up here. So now you can be 500 times cheaper than rockets with mass drivers. And if you put a mass driver on the moon or on Mars to get back, well, then your round-trip costs are like 100,000 times cheaper. So it really does open up the solar system to start using mass drivers to get around, due to this, the economics associated with the physics and cost of mass drivers. So I talked about this variable pitch screw launch mass driver as one of the mass drivers in the class of mass drivers that achieves velocity squared scaling instead of velocity cube scaling. This prototype reveals the principle of operation. You basically have a sled that attaches to the screw magnetically. It magnetically couples without physically touching it. And by coupling to the screw threads accelerate it because they have a variable pitch. So even though they turn at a steady speed, the sled will speed up as it goes down the screw system. Now each of these individual screw segments is powered by its own motor. It's not a continuous screw. They're internally driven, and they just look like a continuous screw. Here's a visualization of it from our digital twin model. You can see the screws are spinning very quickly here. These thin brackets hold each individual screw segment, and there's stuff inside each screw to keep it spinning and to transfer momentum from the electric motors that spin the screws into the launch sled as it moves along. So I said earlier that the older kinds of mass drivers, they change electrical energy into kinetic energy on the fly. Like as you go through each segment, a ton of electrical energy gets dumped out of a capacitor through a bunch of power electronics or power conditioning stuff, and then turns into kinetic energy. Because this vehicle is going faster and faster as it goes down the length of the launcher, by the time you get to the end of the launcher, that conversion has to happen in a split second, like microseconds. And transferring a lot of energy in a short period of time equates to a lot of power. And this is why these other technologies get very expensive as you get to very high speeds. The power electronics at the end of the launcher is incredibly expensive. So you have to solve that problem if you want to make mass drivers economically efficient. The variable pitch screw launcher does this by, it first spins up all the screws and flywheels inside the screws in advance. So there's no expensive power electronics because you're taking a lot of time to speed up the screws. It's just electric motors. The conversion is from a rotational form of kinetic energy to a linear form of kinetic energy, which is done by these screws. Essentially, it's a magnetic worm gear that's converting the rotational energy to linear kinetic energy. But there's no electrical to kinetic energy power conversion, so no power electronics required at that stage. So this is why we can essentially get the cost down to being proportional to the length of the launcher, not proportional to the velocity cubed. All right, this video is generated by our digital twin. It gives you an overview of how it works. The spacecraft rides on a on a maglev track, which is called the guideway. There's this component in the back, which is kind of like the booster stage. It's an adaptive nut. It couples to the screws. It adapts to the geometry of the screws as you travel down the launcher. And then eventually we'll get to it when this gets to the end. We eventually get to the mountain and where the ramp is, and then travel to the elevated evacuated tube. Screws are spinning at speeds that are already proven with other kinds of technologies, rotating machinery, like turbines and jets and things like that. And keep in mind, there's no torque in these screws. A lot of people look at this and go, oh, there's torque all the way down the screws. Now, each individual screw is powered individually, so there's no torque within the screws themselves. And there's no contact between any components because they're all magnetically levitated on magnetic bearings. The only physical contact occurs when the clutches engage between the flywheels and the screws on the inside. So there's like a slight deceleration of the flywheel on the inside, which has mechanical contact. Other than that, it's non-contact. How do you get it through the atmosphere, though? Like, how do you get through the lower atmosphere without burning up? That's a key question. So there's a lot of ideas about how this could be done. What we are proposing is that we use drone technology, since drones are very popular these days, or eVTOL technology, to levitate a large tube up into the atmosphere. And this tube would be evacuated. So it's basically an elevated evacuated tube supported by lift fans. The lift fans are powered by a power plant on the ground, not by batteries that they carry up with them. And there's an airlock at the end that the spacecraft goes through to prevent air getting into the end. And if the weather turns bad, then the screw can actually coil itself up, like it can fly back and coil itself up as it does so, and land in a coil-shaped hangar on the Earth and wait out the storm. Now, a lunar mass driver, similar idea. Like I said, it doesn't need to be nearly as long as the Earth-based mass driver because the velocity need to get into orbit or into the NRHO orbit is just 2.35 kilometers per second, so a much shorter mass driver. You could use rockets to get off the moon, but the problem with rockets is that you've got to mine water ice, which is, we're not even sure it's easy to mine yet. You've got to convert that water ice into hydrogen and oxygen. You've got to have a hydrolox rocket engine, which is a hard type of rocket engine to build. You've got to store the hydrogen. You've got to transport the hydrogen. There's all these reasons why it's difficult to make a rocket launch at scale to launch rockets off the moon. With a mass driver, you're getting direct electrical energy to kinetic energy conversion without any propellant plants in the middle. Now you can also, if you use a variable pitch launcher, you can also fabricate all the parts using materials that are readily available on the moon. So aluminum oxide is the second most common material on the moon, and you can make almost the entire mass driver out of aluminum if you want to build a lunar mass driver. So the advantages, like I just said, the ISRU potential, the mass that you need to ship from Earth to build this mass driver is tiny compared to what you can get off the moon. It's got high electrical efficiency, minimal heat generation. There's no mechanical wear, no inspection or refurbishment needed of this technology. It supports regenerative braking of the adaptive nut, so you can save the power there, part of the efficiency equation. It supports a wide range of g-force versus length trade-offs, so you can accelerate fast and have at high Gs if you want, if you have a robust cargo, or you can accelerate much more gently and have a longer mass driver if you want to launch people or delicate cargoes. It does not emit any EM fields that'll affecting the spectrum or anything like that. It does not attract iron particles. It does not have a lot of big magnets in it. And it's easy to repair. And it's also dual use. You can use it to store electricity on the moon, which is useful too. The traction this technology has so far, we first described it in an IEEE paper, aerospace paper, which is a big conference they have in Big Sky every year. JPL goes there mainly. We talked about it in a paper on tethered rings in 2023. We've written a 20,000 line of code digital twin model of the technology, including a full cost model. And we have a dedicated 21-page paper now on the VPSL part itself, which is published in the IEEE Transactions on Plasma Science in October 2025. Now this journal, by the way, is where it's a watering hole for all the people who deal with pulse power. There's a lot of fusion people there, a lot of experts on high power systems. So these guys are a good peer review community for this technology. We also have the small scale prototype in development, which you saw earlier. And the latest thing we've been doing is something called the Evidence Ledger. The Evidence Ledger is a peer review, like a crowdsourced peer review platform, where we find experts like you to come in and review the individual claims of the subsystems related to the variable pitch screw launch system or any other grand idea. Right now we have 45 claims on variable pitch screw launch, but there's a lot of other concepts in there as well, skyhooks and things like that, that you could review if you're interested in those technologies. Here's a list. It's an eye chart, I know, but here's all the claims that the variable pitch screw launch has. The ones in green have already been reviewed by experts. The remaining ones need to be reviewed. So if you're an expert in something, come see me. We really would love to have your input. Here's what you would see if you dove down into one of those claims. So there's some really technical material inside the claims, also inside the papers, showing the work we've done to validate these ideas. All right, so to conclusions. So NRHO data centers are possibly a plausible technology, but only with extremely low launch costs. I'm almost certain not plausible with Earth-launched chemical rockets. The mass driver on the moon idea might make these NRHO data centers economically feasible. And again, rockets on the moon wouldn't do the job because of all the challenges with refueling the rockets. The variable pitch screw launcher is uniquely suited to the moon. It has this ISRU potential. It's got zero wear. It's infinitely reusable, low magnetic fields, and highly efficient as a technology for accelerating mass. And the traction we've gotten so far, like I said, a couple peer-reviewed papers in really prestigious journals, 20,000 line of code digital twin, prototype, and now the evidence ledger, and all your support as well if you contribute to the evidence ledger. Now, if you're not into all these papers and too much TLDR, there are some videos in the technology. Hello from Space was one author in Australia who did a video on it recently. Isaac Arthur's done a couple videos on it. And then you can find these videos on the Project Atlantis website. There's many more than the 6 I've shown here. And I think that brings me to the end of the presentation. This is the link to the evidence ledger, where I'm hoping to encourage some of you to go and read the claims and hopefully review some of them. So thank you very much, and it's time for questions. So we've got one in the back already, and then you.
How many points of failure are there in the mass driver, and what would you say are the most significant points of failure? Thank you.
Yeah, I think the one that worries me the most is the possibility, like for the lunar mass drive anyway, is the possibility of a micrometeorite hitting a screw as it's running at top speed, and then that screw's fragmenting, and then you'd have a missing screw. I don't think in the lunar case that missing screw would be a problem. I think you could just go past it as long as it wasn't distorted. I think it would just fragment and it would be just missing. So I think that would be okay in the case of the lunar mass driver. On the Earth-based mass driver, there's this chance of that happening and then puncturing, say, the vacuum tube, losing vacuum. That could be pretty disastrous. But in that case, there's no micrometeorite to trigger the action. So if you just do good inspection of the screws, you should be able to get your failure rate down. And you don't need to run these screws at close to the edge of breaking. You can run them with a 30 or 40% engineering margin so that they're not going to break. They're like airplane turbines. They don't break all the time, almost never. Your question was next and after the end. Yeah.
Have you done a cost-benefit comparison with like a lunar space elevator conveyor belt goes from the moon out to near Earth?
I've not actually found anything on the cost of lunar space elevator. I probably should do more research like that, but yeah.
What you have to do is go to Liftport.
Yeah, that's right. Yeah, I know. Yeah.
The point is, they've got something like an evidence ledger too.
Oh, do they?
Yeah, so you guys might want to compare notes.
Yeah, I'll chat. Find Michael in chat, yeah. So I've seen very little in the way of other people doing good cost estimates like we've done, and I encourage more people to do that. I think it's really important to get the economics into a reviewable state and have experts look at it.
So for the Earth-based mass driver, you've got an evacuated tube. How high an elevation do you get with that, and what percentage of the atmosphere are you through before you go through the airlock? I would think it'd be a pretty big shock going from vacuum into any significant atmosphere at all.
Yeah, you're right, and that's something we're studying. So right now we're not 100% sure what the right altitude, the optimal altitude is, but we're saying 15 kilometers for the end of the elevated evacuated tube. So we're pretty sure we can get something to fly 15 kilometers. It's a bit like the Ingenuity helicopter on Mars, not quite as thin an atmosphere as that, but it's pretty thin up there. And then at that altitude, the evidence on heat shield performance in this sort of flight regime I'm sure it's there because nuclear missiles tend to use this flight regime a lot, but it's not publicly available, so it's really hard to find good data on what a heat shield can do if we were exiting the atmosphere from 15 kilometers and going straight up.
Well, if you're that high to begin with, my question is probably a little bit moot because
Yeah, it's not very high, but it's still significant. I mean, your nose cone is going to be white hot for a few seconds, for sure. Yeah.
If you're trying to, on the Earth, raise this long evacuated tube, which I'm assuming is many miles long, right?
Yeah.
I would think you'd have several problems. Number one, there's going to be a significant mass you've got to raise, and you're going to have all these turning things in it.
Yeah.
And
Oh, the screws are not inside the evacuated tube that's in the air. Just that may be a common misconception.
okay,
So the screws that accelerate the system are in the ocean, and they end. And then you go up the ramp. There actually are screws on the ramp to decelerate the adaptive nut, but they're not used for accelerating the spacecraft anymore. The spacecraft is on a sled, much, much lighter. Then when it gets into the elevated evacuated tube, there's no contact between the spacecraft and the tube at all. It's just on a ballistic trajectory. And the tube is maintaining a corridor around the ballistic trajectory.
how does the evacuate, how do you keep the projectile inside the center of that? I mean, you've got this thing you're trying to support with drones that's miles long. How do you make it straight enough, and how do you support any kind of instability? I know it's an evacuated tube, but how do you make sure all that? It sounds to me like a very difficult thing.
It is, yeah. So that's one of the
fails, it's catastrophic.
That's right, yeah. So that is one of the technical challenges that's covered in one of these claims.
Okay.
So we point to things like drone light shows, for example, to show at what precision we can maintain the position of a drone relative to some arbitrary flight path, right? So you have to have some margin. Like the tube has to be bigger than the flight path, obviously, with some margin so that there can be errors. But the assertion is that we can engineer drones to fly accurately enough to keep the tube around the flight path without even the presence of gusts of wind and stuff like that. So that's the assertion, but expert reviewers with experience on atmospheric turbulence and things like that may disagree with us, and so we'd have to get them in there to review it. So
As even kind of small tube, like a few hundred, 1,000 feet or something.
yeah, well, I mean, I think it's easier with a small tube. I mean, obviously you could just attach it to the ground in that case.
Has anybody actually tried it?
No, nobody's. I don't think anybody's tried to make an evacuated tube fly yet, as far as I know.
No.
We're not there yet. No.
Okay.
Yeah.
Could this be used basically to put, say, telescopes, say, farther out in the solar system, say, near the Pluto areas, where you could really study interstellar space with the
I bet it could be.
Yeah.
I haven't studied that though.
Yeah.
But I invite all of you to dream on what you can use it for.
I think this
All right,
year-
I've run out of time, so I'm going to invite my next speaker up, David Dillon.